There's a kind of cosmic explosion that has only shown up 3 times in all of human history, and you've almost certainly never heard of it. Not 3 per year, not 3 per galaxy, just 3 events, total, in roughly 50 years of watching the sky in high-energy light. That is the level of rare we're dealing with. So watch this video till the end and subscribe to the channel. Let's begin. For about half a century, satellites above Earth have been quietly listening for gamma rays, the most energetic form of light. In that time, we've logged thousands of gamma ray bursts from distant galaxies, plenty of supernova explosions, and constant flares from our own sun and from black holes feeding on gas. Those are now routine for space telescopes. But in this entire flood of violent events, there is a tiny subclass called magnetar giant flares. And the truly extreme ones that happened close enough for us to study in detail add up to 3. The first one was in 1979, then another in 1998, and a third in 2004. One came from our neighbouring galaxy, the Large Magellanic Cloud, and the other 2 came from inside the Milky Way. Each one was so bright in gamma rays that it briefly outshone almost everything else in the sky at those energies. Yet if you were standing outside on Earth at those moments, you would have seen absolutely nothing. No new star, no flash, no dramatic streak across the sky. The universe pulled off 3 of the most extreme explosions we've ever measured, and almost nobody outside the space science world noticed. When astronomers say rarest here, they're not exaggerating. Normal gamma ray bursts, especially the ones from merging neutron stars or collapsing massive stars, have been recorded in their thousands. We've built catalogues, classifications, subclasses inside subclasses. Supernovae are standard tools for measuring distances across the universe. But these giant magnetar flares, at the power levels we saw in 1979, 1998, and 2004, show up at a rate of roughly 1 per few decades per galaxy in our instruments. Not just uncommon, they sit at the extreme tail of the distribution. Because of that, every single one became a kind of Rosetta Stone. The 1979 event forced people to admit there was some kind of insanely powerful compact object behind it. The 1998 flare added better timing data and spectra that fit the idea of a neutron star with a ridiculously strong magnetic field. The 2004 flare was so powerful that it basically locked in the concept of the magnetar as a separate type of neutron star. From just these 3 explosions, people built an entire theory for a new class of objects in the universe. So what actually happens during one of these things, in real time? Each giant flare starts with a spike, a sharp blast of gamma rays that lasts around 1/10 to a few tenths of a second. That's it. Less than the time it takes you to blink. In that tiny window, the flare releases something like 10,000 trillion units of energy called ergs, or even 100 times more for the strongest one. If you translate that into solar terms, you're talking about the sun's entire output over hundreds of thousands of years, maybe up to 1,000,000 years, compressed into a fraction of a second and launched out into space as high-energy photons. To a satellite detector, that spike is basically a wall of gamma rays that hits, overwhelms the sensors, and then fades. Instruments can get saturated because the signal is too strong. To your everyday life, it was just a normal day. You didn't feel heat on your skin, you didn't see anything in the sky, the air didn't glow. The whole thing happened far above your head in a part of the spectrum your eyes can't access, and the atmosphere blocked almost all of it from reaching the ground. That's the first reason you haven't heard of these events. They shine mainly in gamma rays and very energetic X-rays, which are completely invisible to human eyes. Our atmosphere does its job and absorbs them, which is good for life, but it means the only way to catch these flares is with satellites above the air. And those satellites are usually built for broad surveys, not for making dramatic news headlines. The second reason is speed. The main spike is over almost instantly, and even the extended tail of X-ray emission that follows lasts only minutes. It's not like a supernova that might stay bright in visible light for weeks. By the time ground-based telescopes swing around to look for any aftermath, the actual flare is done. What they see instead is the fading echo, usually a slowly dropping X-ray brightness, and sometimes a radio afterglow expanding out into space. So you get these absurdly powerful events invisible to your eyes, filtered by the atmosphere, and effectively too fast to feel, unless you're a satellite armed with a gamma ray detector, flying in exactly the right place in orbit at exactly the right time. The universe just fired a magnetic cannon, and you missed the entire thing. That raises the real question. If this isn't a normal explosion like a star dying right now, what is storing that much energy, and how does it release it in under a second? The current answer points to one of the strangest objects we've ever discovered. A tiny neutron star with a magnetic field so strong it can distort matter and even change how empty space behaves. We call it a magnetar, so the mystery deepens. You have a star core crushed down to the size of a city, wrapped in a magnetic field far beyond anything you encounter anywhere else, slowly building stress for centuries, and then occasionally releasing that stress in a single spike that can light up a galaxy in gamma rays. What exactly is a magnetar? How can something that small be that extreme? And why do only a few of them ever produce these three legendary giant flares? Some of the most extreme things in the universe would actually fit inside your city, and that sounds wrong until you meet a magnetar. When you hear star, you probably think huge blazing ball of gas, but a magnetar is basically what's left after a massive star has already exploded and collapsed. The outer layers are gone, the core has been squeezed down, gravity has done its absolute worst. What's left is a sphere only about 20 kilometers across. That's smaller than many cities on Earth, holding around 1.5 times the mass of the Sun. Think about that for a second, not in a poetic way and in a literal physical way. Take the Sun, which could fit more than 1 million Earths inside it, compress its mass to something the size of a city, and you get neutron star material. Now go one step further, twist its magnetic field into something insanely strong, and you have a magnetar. If you could scoop up 1 teaspoon of this stuff and somehow bring it to Earth without destroying everything on the way, that teaspoon would weigh more than 100 million tons. That's heavier than a large skyscraper, in 1 spoon. The matter is packed so tightly that atomic nuclei are pressed together. Electrons are mostly crushed into protons, turning them into neutrons. So you get a giant atomic nucleus held up by quantum physics. So you've got this city-sized core of almost pure neutrons. Now add the part that really breaks your sense of scale, the magnetic field. Earth has a magnetic field of about half a Gauss. That's what makes compasses work. The Sun's average field is just a few Gauss. A bit stronger in sunspots, but still normal by cosmic standards. A magnetar doesn't play in that range at all. Its field goes up to around 10,000 trillion Gauss, even 100,000 trillion in some models. In more familiar units, that's about 1 billion to 100 billion Tesla. To compare, the strongest steady magnetic fields humans can make in labs are in the tens of Tesla range for big machines. Maybe a bit above that in pulsed mode before the coils physically blow apart. A magnetar laughs at that. Its field is so strong that if one somehow drifted within about 1,000 kilometers of Earth, the magnetic forces would literally start messing with the electrons in your atoms. Chemical bonds would not behave the way you're used to. Your body, your electronics, and your planet's upper atmosphere Everything is coupled to this invisible field that's way beyond what normal matter is built to handle. Now here's the twist. You might expect something this intense to be spinning insanely fast, like a cosmic drill bit. Most neutron stars actually do spin like that. A lot of them rotate tens of times per second, some hundreds of times per second. They sweep beams of radio waves across the sky like lighthouses. Magnetars are not like that. They're weirdly slow. Typical magnetar rotation periods are around 2 to 10 seconds per turn. For a neutron star, that's sluggish. But even though they spin slowly, they are braking very hard. We can measure how fast their rotation is slowing down, and it's way faster than in normal pulsars with similar spin rates. That tells you something important. It means their huge magnetic fields are dumping rotational energy into their surroundings at a ridiculous rate. The field acts like a brake, creating strong electromagnetic torques, driving currents in the surrounding plasma, heating up the star's surface and magnetosphere. So magnetars glow strongly in X-rays, not because they're spinning fast, but because their magnetic fields are constantly decaying and releasing energy. So how many of these things are out there? In the Milky Way and nearby galaxies, we've only identified on the order of 30 magnetars so far. That's out of thousands of known neutron stars and out of hundreds of billions of normal stars total in our galaxy. Statistically, magnetars are the weird edge cases. We usually find them only because they have some kind of outburst in X-rays or gamma rays. They sit there quietly for years, then suddenly start spitting out bursts, and our satellites pick up the flashes. Once that happens, we track their pulsations, measure their spin and spin down, and the numbers scream magnetar. There are almost certainly many more magnetars hiding from us. Some are probably too far away, buried behind dust, or in a quiet phase with no bright bursts. But the fact that we've only confirmed about 30 tells you that active magnetars are already rare. And among that rare set, the ones that produce giant flares like the 3 legendary events we're talking about, are rarer still. Now we get to the dangerous part of their personality. A magnetar is not a stable object just calmly sitting there. Its enormous magnetic field is twisted and stressed. Deep inside the star, currents are moving. The field is slowly reconfiguring over thousands of years. The solid crust of the neutron star is locked to this field. As the field changes, it drags on the crust, twists it, builds tension. Picture it less like a bomb with a simple fuse, and more like a solid shell being slowly over-torqued. For a long time nothing obvious happens. The crust holds. The magnetic field stores more and more energy. Every so often that stress gets released. Sometimes the release is small. You get a short burst of X-rays or soft gamma rays, a tiny crack in the crust, a local rearrangement of the field. We call those bursts and flares, and they can repeat over and over from the same magnetar. But in rare cases, the stored magnetic energy is so high and the instability so global that the star undergoes a much larger failure. The crust fractures over a wide region, the magnetosphere reconnects, and a huge amount of magnetic energy is dumped into a hot plasma in a very short time. That is when you get a giant flare. So a magnetar is basically a metastable bomb. It is not exploding like a supernova and destroying itself. But it is always one big magnetic rearrangement away from releasing a chunk of energy that can temporarily dominate a whole galaxy in gamma rays. It can do that without dying, but it cannot do it often. Each giant flare costs a serious piece of its magnetic energy budget. That leads to the next step in the story. If magnetars spend most of their lives quietly building up this tension, what are the smaller warning signs before one of these rare giant flares? And how did we first notice that some magnetars like to repeat in softer gamma rays long before they go all out? Before a magnetar throws one of those giant flares you heard about, it usually doesn't start with the biggest punch. It starts with warning shots. That's where soft gamma repeaters come in, and they're basically the early angry phases of a magnetar you've pushed too far. Soft gamma repeaters, or SGRS, are sources in space that keep spitting out short bursts of high-energy radiation. Soft here doesn't mean gentle. It just means the gamma rays are at slightly lower energies than the hardest classical gamma ray bursts. Each burst lasts around 1/10 of a second, sometimes a bit less, sometimes a bit more. During that tiny slice of time, an SGR can release something like 10 to 100 trillion ergs of energy. In more normal words, each little SGR burst can be far more energetic than the biggest solar flares the sun has ever thrown at Earth. And SGRs don't just do this once, they repeat. That's literally the name. When an SGR goes into an active phase, it can fire off dozens or even hundreds of these mini bursts over days or weeks to a gamma ray satellite. That looks like a machine gun of short spikes, each one insanely bright compared to the usual background. To you on Earth, again, nothing obvious, no visible flash in the sky, no shock wave. All the drama is happening in a band of light your eyes cannot pick up, filtered by the atmosphere, and recorded as data streams going into hard drives. Here's the important pattern. Historically, every time we have clearly seen a true giant magnetar flare in our local neighbourhood, it came from an object that had already been acting like a soft gamma repeater. First, it has a storm of these smaller bursts, this active chatter phase. Then, rarely, it produces one huge spike that is orders of magnitude more powerful. It's a bit like a fault in Earth's crust that has lots of little earthquakes, then eventually drops a big one. The smaller bursts tell you the system is stressed. The giant flare tells you that stress finally crossed some breaking point. So how do we know that these SGRS are tied to individual neutron stars and not just some random cloud of hot gas? The key clue is timing. Many bursts, and especially the giant flares, don't just fade smoothly, they have pulsating tails. After the initial spike, the X-ray brightness goes up and down in a very regular rhythm. Those pulses usually repeat every few seconds, between about 2 and 12 seconds depending on the source. That repetition rate matches the rotation period of the magnetar. The idea is simple. The flare creates a hot cloud of plasma trapped close to the star's surface by its magnetic field. As the magnetar rotates, we see more or less of that glowing region, so the X-ray flux rises and falls periodically. By measuring those pulses, we are effectively timing how fast the neutron star is spinning. This is one of the strongest pieces of evidence that SGRS are not just diffuse explosions in space, but are coming from compact spinning objects. Then there's an extra layer of detail buried in the tails of the really big flares. When astronomers studied the 1998 and 2004 events very carefully, they noticed that the X-ray brightness was not just pulsing every few seconds, it also had tiny wiggles at much higher frequencies, tens to hundreds of times per second. These are called quasi-periodic oscillations. Quasi because they're not perfectly stable tones. They drift a bit in frequency and strength. The best interpretation is that these are vibrations of the neutron star itself. The giant flare doesn't just light up the magnetosphere, it cracks the solid crust and shakes the whole star. Different vibration modes ring at different frequencies, a bit like different ways a bell or a drum can vibrate. In a magnetar, those modes are controlled by things like crust thickness, density, and how the magnetic field threads through the interior. When we pick up those oscillations in the tail of a flare, we're basically recording the star's internal ringing after a massive quake. It's direct evidence of a starquake shaking an object 20 kilometers wide from tens of thousands of light years away. That turns SGRs into more than just noisy sources in gamma-ray catalogues. They become tools. Every short burst tells you the magnetar's magnetic field is rearranging on a small scale. Every active phase tells you the object is in a high-stress state. Every pulsating tail gives you a clean measurement of its spin period and how that period changes. And every detected oscillation during a flare tail gives you clues about the star's interior structure, something we cannot get any other way. So where does this leave the three legendary giant flares? Those are not random on-off freak events disconnected from everything else. They sit at the very top end of the SGR behavior spectrum. Most of the time, a magnetar vents its stress through smaller bursts, the kind you'd file under normal SGR activity. Very rarely, all the conditions line up for something larger, more global, and far more violent. Then you get one of these monster flares, releasing a bigger fraction of the magnetic energy in one shot. That's the picture to keep in your head. Soft gamma repeaters are the warning shots. The everyday tantrums of a magnetar that is constantly being twisted by its own magnetic field. Giant flares are the once in decades or once in centuries meltdown, when the internal tension and the magnetosphere shift in a way that dumps an absurd amount of energy almost instantly. From your point of view on Earth, the difference between a normal SGR burst and a giant flare is just a ratio in brightness and duration in a data file. From the star's point of view, one is a crack in the shell, the other is a partial reset of the whole system. And that brings us to the first time humanity actually got ambushed by one of these things. Back in 1979, a set of spacecraft scattered around the solar system all got hit by a sudden blast of gamma rays within fractions of a second of each other. No one knew what had just gone off, or where it came from. How do you track down a single explosive event across interplanetary space, and how did that mystery turn into the first confirmed magnetar giant flare? On March 5, 1979, the solar system quietly set a record without anyone on Earth noticing in real time. Far from the headlines, a bunch of spacecraft scattered around the inner system all got hit by the same sudden blast of gamma rays. These weren't built as some coordinated experiment, they were different missions with different goals. Venera, Helios, Pioneer Venus, Vela, ICE 3, but in their data, within fractions of a second of each other, they all recorded the brightest extra solar gamma event anyone had ever seen at that point. For the instruments on those satellites, the signal was brutal. A sharp spike of gamma rays arrived out of nowhere, way above the usual background level. Some detectors saturated, meaning the signal was so strong they basically maxed out. This was not the sun having a normal flare. It was too bright, too fast, and it hit every satellite regardless of where it was in its orbit. Whatever went off, it was incredibly far away compared to anything inside the solar system, but still bright enough that even detectors built for nuclear test monitoring and general space science got hammered. Once people realized they all had seen the same event, the obvious next question was where it came from. Gamma ray detectors don't take pretty pictures. They mostly count photons over time. You don't get an immediate, here's the exact spot in the sky. But there was one big advantage on that day. The spacecraft were spread out over millions of kilometers. That meant the wavefront of gamma rays would not hit all of them at the exact same instant. The tiny differences in arrival times became the key. By lining up when each satellite saw the spike, astronomers could draw time delay curves and figure out which direction the wavefront was coming from. That process, triangulation, is the same idea as using multiple cell towers to find a phone. From those timing differences, they trace the origin back to a region in the sky that contained a known supernova remnant called N49. N49 sits in the Large Magellanic Cloud, a small galaxy orbiting the Milky Way, at a distance of about 50,000 parsecs, roughly 163,000 light-years. So now you have a location and a distance. With that, you can turn "this was bright in our detectors" into "this is how much energy the source must have emitted." At that distance, the inferred energy output in gamma rays alone was around 10 to 100 trillion ergs during the initial flare. That is already hard to process. You're talking about a compact object that dumped more energy in a fraction of a second than our sun emits over tens of thousands of years. And here's a detail that quietly raises the stakes even more. That 1979 source was in another galaxy. Later, when we found the 2004 giant flare from SGR 180620 inside our own galaxy at something like 50,000 light-years, you can compare. If you hypothetically moved the 1979 event to that closer distance, it would have been orders of magnitude brighter in our sky. So even though the 1979 flare was record-breaking at the time, it probably wasn't the most extreme possible version of this phenomenon. It was just the first one we were lucky enough to catch. Back in 1979, no one instantly said, "This is a magnetar giant flare," because the magnetar concept wasn't fully formed yet. People knew about neutron stars, they knew about regular pulsars and X-ray binaries, but this thing didn't fit the usual categories. It were way too energetic for a solar flare. It didn't look like the classical gamma ray bursts that were being catalogued, which were usually shorter and did not show the same follow-up behaviour. The key clue was in the tail. After the initial spike of gamma rays, the source did not just shut off. There was a decaying tail of X-ray emission that lasted for minutes, and that tail was pulsing. The brightness went up and down with a period of about 8.1 seconds. That is exactly the kind of timescale you expect from a rotating neutron star. So you have a compact object somewhere in a young supernova remnant in another galaxy, pulsing every 8 seconds, that has just released this ridiculous burst of gamma rays. Over the next decade or so, theorists like Christopher Thompson and Robert Duncan pushed a new idea to explain this combination of features. Instead of a neutron star powered mainly by its rotation or by accreting gas from a companion, they proposed an ultra-magnetized neutron star where the main energy source is the decay of a super-strong magnetic field. That decay twists the crust, powers bursts, and in rare cases drives a giant flare like the one seen in 1979. That was the birth of the modern magnetar model. Once that connection started to look plausible, the attitude in the high-energy community shifted. This was no longer just a weird one-off event in old gamma-ray records. It became the prototype of a potentially new class of explosions. After 1979, people started building watch lists. They tracked sources in and around 49, they monitored other soft gamma repeaters, they improved gamma-ray monitors on future missions and set up networks to compare data quickly when something bright went off. The idea was simple. If the universe did this once, it might do it again, and next time we wanted better data. But then, nothing like it showed up for a long time. There were gamma-ray bursts, sure, many of them. There were solar flares, there were SGR bursts of lower energy. But for almost 2 decades, no other event matched the combination of intensity and pulsating tail that defined the March 5, 1979 flare. That silence was itself an answer. It told astronomers that whatever magnetar giant flares are, they are not everyday explosions. They are rare even on magnetar timescales. So by the late 1990s, you had one giant flare in another galaxy that didn't fit the usual boxes. A growing theoretical picture of magnetars as ultramagnetic neutron stars, and a long gap with no second example. The pressure was building. Would we ever see another flare like 1979 again? Would it confirm the magnetar idea, or force us to rethink it? And what would it look like if it happened inside our own galaxy, instead of in a companion galaxy far away? For almost 20 years after 1979, astronomers waited for another blast on that level. Then on August 27, 1998, space quietly hit a new high score. The source was called SGR 1900+14, and the flare it produced that day became, at that time, the most intense gamma-ray flux ever recorded from a single known object in the sky. When this thing went off, detectors on multiple satellites basically lost their composure. Missions like Beppo, SAX, and WIND saw their instruments saturate. The incoming signal was so strong that the detectors hit their maximum count rate and flattened out. That's how you know you are way outside normal territory. These instruments are built to handle bright gamma-ray bursts, solar events, cosmic backgrounds. For SGR 1900+14, many of them just clipped. The data literally said, "too much." Now here's the part that connects this to you directly. SGR 1900+14 is roughly 10 kiloparsecs away, close to 20,000 light-years. That's far. It lives in the outer region of our galaxy, nowhere near the solar system. And even from that distance, this flare physically changed Earth's atmosphere. The sudden flood of gamma rays and X-rays ionized parts of the upper atmosphere, meaning it stripped electrons from atoms, changing the conductivity of the ionosphere. Radio waves that bounce off that layer behave differently. For a short time, our planet's electric skin responded to a neutron star halfway across the galaxy having a bad day. If you plot the brightness of this event over time, you see the classic magnetar giant flare pattern. First you get an incredibly sharp spike, lasting around 0.3 of a second. That's the main blast, the initial release of magnetic energy. Right after that, instead of dropping to zero, the emission settles into a tail that lasts for several minutes. And that tail is not smooth. It rises and falls in a regular pattern, with a period of about 5.16 seconds. That number is the spin period of the magnetar, every 5.16 seconds. The rotating neutron star brings the brightest part of the trapped fireball into and out of view. Add up all the gamma-ray energy from the spike and the tail, and you get another huge number, roughly 10 to 100 trillion ergs again, in the same ballpark as the 1979 flare. Different instruments and models give slightly different totals, but you're solidly in that 10 to the 44 to 10 to the 45 erg range. Once again, a single compact object has released in less than a minute what the Sun would need tens of thousands of years to emit. The details of the spectrum tell you even more about what's happening near the star. This flare wasn't just soft gamma rays. There was a hard tail reaching up to hundreds of kilo-electron volts, roughly in the 300 to 650 kilo-electron volt range, and some analyses hint at photons going up to around 10 mega-electron volts. That's a signature of a very hot plasma of electrons and positrons, plus high-energy gamma rays, confined close to the star by an ultra-strong magnetic field. The field strengths you need to trap that kind of pair plasma and keep it from just exploding away are in the 10 to the 14 to 10 to the 15 Gauss range, exactly what the magnetar model predicts. So you have multiple layers of evidence stacking up. The light curve shape matches the idea of a sudden magnetic reconnection event, followed by a cooling, trapped fireball. The period of the pulses in the tail matches the rotation of a neutron star. The spectrum matches a very hot pair plasma held in by a huge magnetic field. And then there's one more piece. the tiny flickers buried in the tail. When people dug into the X-ray data from this flare, they found quasi-periodic oscillations, small variations in brightness at specific higher frequencies, tens to hundreds of cycles per second. These aren't just noise, they line up with theoretical expectations for vibration modes of the magnetar's crust and interior. Think of it as the star ringing after a massive fracture. The giant flare cracks the crust, the entire object shakes in different patterns, and those vibrations slightly modulate the X-ray flux we see. From our point of view 20,000 light years away, we are basically doing seismology on a star. Instead of using ground motion sensors like we do for earthquakes, we use space telescopes measuring X-rays. Each identified oscillation frequency tells you something about the stiffness of the crust, the density, how the magnetic field is arranged inside. You don't see the star moving physically in a telescope image, but you see its brightness jitter in very specific ways that match models of starquakes. By the end of the 1998 event, the message was clear. Whatever went off in 1979 was not unique. The galaxy had now produced another giant flare, this time from a magnetar firmly located inside the Milky Way. The pattern of spike plus pulsating tail, the enormous total energy, the hard spectrum, the quake-like oscillations, all pointed in the same direction. Magnetars were real, and when they let go, they could dominate the high-energy output of the entire sky for a few seconds. But the universe still had one more escalation planned. If a magnetar 20,000 light-years away can saturate our detectors and punch our ionosphere, what happens when a stronger one, roughly 50,000 light-years away on the far side of the galaxy, decides to unleash an even bigger flare, one that pushes the energy scale up by almost 2 orders of magnitude? On December 27, 2004, something on the far side of the Milky Way lit up space so hard that our detectors basically freaked out. The source is called SGR 1806-20. It is roughly 50,000 light-years away, buried in a crowded region near the plane of our galaxy. From that kind of distance, you would expect even a powerful explosion to look modest in our instruments. This one did not. For a brief moment, in gamma rays, it became the brightest extrasolar event ever recorded. Multiple satellites saw the spike hit almost at the same time. Their gamma-ray detectors shot straight up to maximum counts, many of them saturated, and then slowly came back down as the flare faded. That is how extreme the flux was. These instruments are designed to handle bright gamma-ray bursts from distant galaxies. Yet this flare from a single magnetar in our own galaxy still pushed them to their limits. When people later compared it with previous records, it was clear this was a new benchmark for how intense a discrete source could look in gamma rays. The raw energy behind that brightness is on another level. For the initial spike alone, in less than 1 second, the estimated energy release in gamma rays was on the order of 2 × 10⁻46 ergs. To keep it in everyday language, that is about 100 times more energetic than the already huge 1998 flare from SGR 1900+14. If you convert that into the energy the sun radiates in all directions, you're looking at what our sun would put out over somewhere around 100,000 to 1,000,000 years, blasted out in under a second. And that is just the spike, not counting the longer tail. Remember the distance here. This magnetar is about 50,000 light-years away, on the opposite side of the galaxy. Yet the blast was so intense that Earth still felt it. The incoming gamma rays and hard X-rays hit the upper atmosphere and ionized it, stripping electrons from atoms in the ionosphere. That changed how radio waves bounced off those layers, and instruments that monitor Earth's ionosphere saw a clear disturbance. So even from halfway across the Milky Way, a small dense star managed to poke our planet and leave a measurable signature in the way our atmosphere conducts electricity. After the initial spike, the flare followed the now familiar giant flare pattern. The brightness crashed down from the peak into a tail of X-ray emission that lasted several minutes. That tail was not steady, it pulsed. The flux rose and fell with a period tied to the magnetar's rotation, roughly a few seconds per cycle. Each pulse corresponded to the star spinning once and sweeping its trapped hot plasma region through our line of sight. This repeating pattern is one of the big reasons we are confident we are looking at a rotating neutron star, not some random expanding cloud. What made the 2004 event even more useful scientifically was what happened afterward. There was a strong radio afterglow. Radio telescopes picked up emission from the region around SGR 1806-20 that brightened, then expanded in size with time. By tracking that expansion, astronomers measured apparent speeds of around a third to maybe two-thirds of the speed of light. That indicates that material was actually thrown out in a relativistic outflow, not just heated in place. The radio emission itself was synchrotron radiation, produced by fast-charged particles spiraling in magnetic fields. That is a classic signature of relativistic plasma. You're seeing a bubble of magnetized material, launched by the flare, ploughing into the surrounding environment and lighting up as it goes. This fits nicely with the idea that a giant magnetar flare is not just light appearing out of nowhere. It is a genuinely magnetically driven explosion that ejects particles and fields into space. When you put the pieces together, the 2004 flare becomes a kind of reference event. You have the most intense gamma-ray flux ever recorded from a single source at that time. You have a huge energy dump in less than a second. You have a clear impact on Earth's ionosphere even at 50,000 light-years. You have a pulsating X-ray tail anchored to the magnetar's spin, and you have a radio afterglow that lets you literally map the expanding fireball. All of that lines up with the magnetar giant flare model in a way that is hard to argue with. By the end of this story arc, you now have 3 confirmed giant flares in our local cosmic neighbourhood. The March 5, 1979 event from SGR 0526-66 in the Large Magellanic Cloud, the August 27, 1998 flare from SGR 1900 plus 14 inside the Milky Way, and the December 27, 2004 superflare from SGR 1806-20 on the far side of the galaxy. 3 different magnetars, 3 monster explosions, all showing the same basic pattern of spike plus pulsating tail, all demanding ultra-strong magnetic fields to make sense. Across decades of observations, with many satellites scanning the sky, and with dozens of magnetars now known in and around the Milky Way, only these 3 events clearly hit that giant flare level in our local group of galaxies. That is where the only 3 found idea comes from. It is not that magnetars are rare by themselves, though they are. It is that giant flares of this magnitude are so infrequent that in about 50 years of gamma-ray astronomy, our instruments have only caught 3 of them close enough to study in detail, so you are left with a question that pushes the tension higher. If magnetars are scattered all through galaxies, and they are constantly shifting their magnetic fields and cracking their crusts, why have we only seen 3 truly giant flares nearby? How often do these magnetic bombs actually go off in a galaxy like ours, and is the universe hiding many more of them just out of our reach? Here's the part that sounds almost too low for how violent these things are. The best estimates say a single magnetar might only fire off a true giant flare once every 50 to maybe 500 years. Not every decade, not every year. once in a chunk of time that's big on human history scales. The exact number depends on how strong its magnetic field is, how it's twisted inside, and how old the star is. Some magnetars might never reach the right conditions at all. Now take that rate and multiply by maybe a few dozen active magnetars in the Milky Way. You end up with at most a handful of giant flares per century in a galaxy like ours. Suddenly, only 3 in 50 years in our local neighbourhood doesn't sound crazy. It sounds about right. Now look at how long we've actually been paying attention. Gamma-ray detectors in space really only started in the late 1960s and 1970s. First for monitoring nuclear tests, then for astrophysics. Early instruments had narrow fields of view, limited sensitivity, and often saw just a slice of the sky at any given time. Over the decades we got better missions, things like Fermi GBM, Swift, Integral, with all sky monitoring and much better time resolution. But even today, we miss events. Satellites are in Earth's shadow, a detector is turned off, a flare happens outside the field of view. We're taking a tiny time sample of a huge galaxy with patchy coverage over only about half a century. That means two big things. First, the true rate could be higher than what we've directly seen. Second, 3 events in that short window is already a lot. If the once every 100 years per magnetar kind of number is roughly right, you shouldn't expect dozens of giant flares popping up in one human lifetime. You'd expect roughly what we have, a few records that stand out among thousands of ordinary bursts. Then there's geometry, and geometry is cruel. These flares probably do not radiate equally in all directions. The gamma-ray fireball is likely at least somewhat beamed, focused into certain angles relative to the magnetic axis. If you're not inside that beam, you either see a much weaker event, or you miss it entirely. So even if a magnetar produces a giant flare on the far side of the galaxy, Earth might not be lined up with the main beam. That flare still happened. It just never hits our detectors in a way we'd recognize as, wow, that's a giant flare. This is also where things get confusing with short gamma-ray bursts. Some extragalactic giant flares may reach us from nearby galaxies, but because they're farther away, and because their emission is beamed, they show up in our catalogues as short, hard bursts that look a lot like neutron star merger events. Unless we get extra clues, like a pulsating tail or a clear host galaxy at the right distance, they just get filed under short GRB and that's it. Distance is the next filter. We can only be really confident that something is a magnetar giant flare if it is close enough and bright enough that we can measure its tail, see the pulsations, and tie it to a known galaxy or even a known magnetar. That basically limits us to our galaxy, its satellites like the Large Magellanic Cloud, and a few nearby galaxies within a few megaparsecs. Beyond that, the giant flare spike blends into the wider zoo of mysterious short bursts. You still detect the flash, but you lose the detailed fingerprints that say, this is a magnetar. So when people say we've only found 3, what they really mean is we've only found 3 nearby events where we can clearly prove they are magnetar giant flares. There are probably more out there in other galaxies. But at those distances we mostly see just the spike, not the whole structure. Without the pulsating tail, and without a clean distance, it's easy to mislabel them. Even with that tiny sample, you can start doing statistics. Researchers go back through decades of gamma-ray burst archives, hunting for events that look suspiciously like giant flares. Very bright, very short spikes, maybe with a soft tail, coming from directions where there are nearby galaxies. They also flip the logic and use non-detections. For example, If you stare at a big galaxy cluster like Virgo for millions of seconds of observing time and never see a giant flare from it, that puts an upper limit on how often each galaxy in that cluster can produce one. Combine all of that, and the picture that comes out is fairly consistent. Giant magnetar flares powerful enough to match the 2004 event are extremely rare per galaxy, and they're much rarer than normal supernovae or standard gamma-ray bursts. They sit in the far tail of the distribution of high-energy explosions we can actually classify. So only 3 found isn't just a catchy phrase. It's a hard-won statistical reality based on decades of watching, searching, and even counting all the times we did not see something. But this raises a deeper question. If these flares are so rare, yet so powerful, then the magnetic fields inside magnetars must be storing and moving insane amounts of energy for long periods, waiting for the right instability to hit. So what is space actually like in the immediate neighbourhood of a magnetar? What does a magnetic field 1 trillion times stronger than Earth's really do to matter and to light? Inside the magnetic field of a magnetar, the rules you're used to just don't apply anymore. You're not just dealing with a strong magnet that tugs on metal objects. You're dealing with a field so intense that the field itself stores a ridiculous amount of energy. Enough that you can talk about the magnetic field having an effective mass. Here's the basic idea. Any magnetic field carries energy. The stronger the field, the more energy per unit volume. In a magnetar, surface fields can reach around 10 billion Tesla, which is 10 to the 10th power in scientific shorthand. If you take that energy density and convert it into an equivalent mass density using Einstein's relation between energy and mass, you find something wild. The energy stored in the magnetic field alone can correspond to a density greater than solid lead. That means when you look at a magnetar, you're not just seeing matter plus a small helping of magnetism. You're looking at an object where magnetic energy is on the same level as the heat energy inside the star, and can even compete with the energy stored in its rotation. So inside the star, there is this huge magnetic reservoir threaded through ultra-dense matter. The field lines are twisted, tangled, anchored into the crust and the core. As the star evolves, that field slowly changes and decays, constantly leaking energy into the surroundings. That is why magnetars glow so brightly in X-rays even when they are not bursting. The magnetic field is not a side effect, it's one of the main power sources. Now zoom in further, to the level of atoms. Under normal conditions, atoms are kind of fuzzy spheres. Electrons orbit the nucleus in all directions, the cloud is roughly round. Once you crank the magnetic field above about 100,000 Tesla, things stop being round. The field forces the electrons to move in tight spirals around the field lines, compressing the atoms sideways. The atom stretches along the field direction and gets squeezed in the other directions. Instead of a sphere, you get something long and thin, like a microscopic needle. At magnetar field strengths around 10 billion Tesla, that effect is extreme. A simple hydrogen atom becomes around 200 times narrower than usual. The electron is squeezed into a very tight tube along the magnetic field line. Energy levels change, allowed orbits change, and the normal rules of chemistry basically break. Molecules cannot form and bond the way they do on Earth. So if you could somehow hold a piece of magnetar surface material in place without all the other insane conditions, the atoms there would be nothing like the atoms in your body. The super strong field rewrites atomic structure. It doesn't stop there. Even empty space behaves differently. In the magnetar environment, you also have to worry about quantum electrodynamics, the theory of how light and charged particles interact. At field strengths above a certain critical value, roughly a few times 10 trillion Gauss, the vacuum itself becomes what's called birefringent. That means it acts like a special kind of crystal that treats different polarizations of light differently. Light passing through this region gets split into two modes that travel slightly differently. So the nothing around the magnetar actually has optical properties. In such fields, even single high-energy photons can do strange things. A gamma-ray photon can split into two lower-energy photons, or two photons can merge into one. Processes that are forbidden or ridiculously unlikely at normal field strengths. Near a magnetar, those processes start to matter. They shape how the spectrum of X-rays and gamma rays looks when it finally escapes. So when we analyze the light curves and spectra of magnetar bursts, we're indirectly probing these extreme quantum effects in the vacuum around the star. Now connect that environment back to the solid crust. A neutron star has a rigid outer layer, a crust made of dense nuclei and degenerate electrons, sitting on top of a more fluid interior. The magnetic field lines are anchored in that crust. As the internal field slowly shifts and decays, it drags against the solid layers. That twist builds up stress, the way twisting something tough like a steel sphere would if you could grab it and force it to rotate slightly differently at different depths. The crust resists, stores elastic energy, and stays locked in place until the stress reaches the breaking point. At some critical moment, the crust can no longer take the load. It fractures. This is not a gentle crack. Huge patches can slip, releasing stored elastic energy and suddenly changing the configuration of the magnetic field at and above the surface. That rapid rearrangement can trigger magnetic reconnection in the magnetosphere, where field lines break and reconnect, dumping even more magnetic energy into a hot plasma made of electrons, positrons, and gamma rays. This is the kind of event we call a starquake. Put all of that together and you get the recipe for a giant flare. Step 1. Start with a neutron star whose magnetic field is insanely strong, so strong that its energy rivals the heat and spin of the whole star. Step 2. Let that field evolve and twist over thousands of years, building up tension in an ultra-hard but finite crust. Step 3. Reach a point where some instability hits, the crust snaps and the magnetosphere rearranges in a big way. Step 4. A huge chunk of that magnetic energy gets converted almost instantly into a trapped fireball of high-energy particles and gamma rays. From the outside, you see that as the spike lasting maybe 0.2 of a second, followed by the pulsating tail. From the inside, it's a magnetic bomb going off. Not enough to destroy the star outright, but more than enough to release in a flash what a normal star would take hundreds of thousands of years to radiate. And you are still only seeing the rare top end of the process, which naturally leads to the next question. If these flares are triggered by cracking the crust of a neutron star, what does that crust actually look like? How strong is it? And what happens during one of these starquakes when the hardest material in the universe finally fails? Neutron stars don't just have strong gravity and strong magnetism, they also have one of the hardest solids in the universe sitting on top of all that. The crust of a neutron star is a solid lattice of atomic nuclei and electrons packed to extreme densities. When people run simulations of how strong that lattice is, they find that its breaking strain is way higher than anything like steel. Steel will deform and crack under high stress. Neutron star crust can hold much more before it gives way. But the key point is, it's not infinite. It has a limit. That means it can store a huge amount of elastic energy, and when it finally fails, it fails in a big sudden way. That sudden failure is what we call a starquake. Now link this to the magnetar field you just heard about. Inside a magnetar, the magnetic field is not calm. It shifts slowly over years to thousands of years, driven by currents in the dense interior. Those changes twist the field lines. Because the field is anchored in the crust, that twist gets transferred into the solid layer. Different parts of the crust are being tugged in slightly different directions, very slowly, all the time. The crust tries to stay locked, but stress keeps building. As the stress rises, the crust starts to approach its breaking point. At some critical level, it can't deform elastically anymore. It fractures, not in one clean line, but in multiple patches and segments. These fractures can propagate around the star, changing how the magnetic field is connected between different regions. That sudden shift in the field geometry can trigger magnetic reconnection in the magnetosphere above the surface, where field lines snap and reorganize. That process is very efficient at converting stored magnetic energy into a hot plasma and high-energy radiation. So you get a direct chain, long-term magnetic twisting, crust fracture, reconnection, giant outburst. The evidence that this really happens does not come from pictures, it comes from timing. During the 1998 and 2004 giant flares, X-ray telescopes didn't just see the bright tail with pulses every few seconds, they also saw smaller, faster wiggles riding on top of that signal. When you take the light curve and analyze it in frequency space, you find peaks at specific frequencies, around 18 Hz, 30 Hz, 90 Hz, and in some data even above 600 Hz. These are the quasi-periodic oscillations people talk about. Those frequencies are not random. They match what you would expect from different vibration modes of a neutron star's crust and core, especially torsional modes, where parts of the crust twist back and forth relative to each other. Some modes involve mostly the outer crust, others couple the crust and the core. The very high-frequency ones likely involve more complex internal motion. In other words, the flare doesn't just light up the outside, it hits the star hard enough to wring its whole structure. This is where the term asterosismology comes in. On Earth, we study the planet's interior by looking at how seismic waves travel through it after earthquakes, by measuring which frequencies show up and how fast different waves move. We infer the structure and composition deep below the surface. With magnetar flares, we are doing the same kind of thing, but with a star. The oscillations modulate the X-ray brightness, and by reverse engineering those frequencies, physicists get clues about crust thickness, how stiff the matter is, whether parts of the core behave like a superfluid, and how the magnetic field threads through the star. The crazy part is that we got this information from just 3 giant flares. Each one gave us a set of seismograms recorded in gamma rays and X-rays, instead of ground motion. It's a huge amount of physics squeezed out of very few events. That is why those light curves have been analysed again and again, because every bump and wiggle encodes something about matter at densities you cannot reproduce in any lab. Now step back and think about the energy budget. Every time you have one of these major starquakes that drives a true giant flare, you're liberating something like 10 to the 44 up to 10 to the 46 ergs of energy in radiation and particle outflows. That is a serious chunk of the magnetar's magnetic reservoir. If a magnetar did that every year, or even every decade, its field would decay very quickly, and it would stop being a magnetar in a short cosmic time. The field would relax, the bursts would stop, the star would cool and fade into the background population of quiet neutron stars. This is one more reason models land on the once per decades to once per centuries rate for true giant flares. The crust can only store so much elastic energy before a catastrophic quake. The magnetic field can only supply so much power over its active lifetime. Smaller bursts and moderate flares can happen more often. They tap the reservoir in smaller bites. But the really big failures, the ones that shake the whole star and light up a galaxy in gamma rays, have to be rare or the system runs out of fuel. So now you have the full chain from deep inside the magnetar to the data on our satellites. Magnetic stress builds, the crust twists and finally snaps, the star rings, and a huge fraction of magnetic energy is dumped into a hot plasma that shines mostly in gamma rays for a fraction of a second. That brings us to the next layer of the story. Once that energy is dumped into plasma near the star, how does it actually turn into the specific spike and tail we observe? What does that trapped fireball look like, and how does it cool and fade in real time? Right after a magnetar crust snaps, all that stored magnetic energy has to go somewhere, and it does not leak out gently. The best picture we have is that it creates a compact fireball, a bubble of insanely hot plasma made of electrons and positrons and gamma-ray photons trapped close to the star by its magnetic field. Temperatures jump to around 1 billion degrees, which is the kind of temperature where the typical photon energy is in the hundreds of kilo-electron volts. Deep in the gamma-ray and hard X-ray range, the field lines act like a cage, wrapping around the star and keeping this fireball from just streaming away into space in every direction. The part you actually see as the brutal 0.2 second spike is the first moment when that energy is dumped into the plasma. Magnetic reconnection near the surface, combined with the mechanical snap of the crust, injects energy so fast that the plasma becomes optically thick, meaning even light has trouble escaping. For a brief instant, the fireball expands at relativistic speeds, close to the speed of light, trying to blow outwards. The magnetic field resists and reconfines it, squeezing it into a compact region above the surface. During that expansion and squeeze, the gamma-ray brightness seen by our satellites rockets up to its peak, then crashes back down. That sharp spike is the signature of an almost instantaneous release of magnetic energy, not a slow burn. Once the spike is over, the system does not just shut off. You are left with that hot, trapped bubble of plasma hugging the magnetar. It is still blazing in X-rays, but now the main job is to cool and shrink. Over hundreds of seconds, the fireball radiates away its energy as X-ray photons, slowly contracting as the pressure drops. Because the plasma is confined by closed magnetic field lines, it can only leak energy through radiation, not through freely expanding gas. When you fit models of a contracting to cooling fireball to the observed light curves, especially for the 1998 flare, the match is surprisingly good. The brightness drops in a way that lines up with the surface area of the bubble shrinking and the temperature sliding down from hundreds of kilo-electron volts to just a few kilo-electron volts. But in these conditions, light itself behaves differently. The magnetic field near the magnetar surface is above what is called the quantum critical field, around 4.4 times 10 to the 13th Gauss. In that regime, quantum electrodynamics says that photons can do strange things. A single high-energy photon can split into 2 lower-energy photons. 2 lower-energy photons can merge into 1 higher-energy photon. The way photons scatter off an electron stops looking like the usual textbook case. All of this affects the spectrum. It tends to push the emission toward a certain temperature range in the tail, a few kilo-electron volts, and shapes how the high-energy end of the spectrum looks. So the light curve and the spectrum together are not just telling you there was a fireball, they're telling you this fireball was sitting in a magnetic field so strong that even the vacuum acted like a weird optical medium. On top of the trapped fireball and its cooling tail, there is also action farther out. Some giant flares, especially extragalactic ones like the event labeled GRB 2004-15A, show high-energy afterglows reaching into the giga-electron-volt range. Instruments like the Fermi Large Area Telescope have seen gamma rays with energies in the giga-electron-volt band lasting hundreds of seconds after the initial spike. That tells you particles are being accelerated to extreme energies in the magnetar's magnetosphere and in the shock where the outflow slams into surrounding material. The afterglow is the footprint of that collision zone, where electrons spiral in magnetic fields and upscatter photons to very high energies. So from the instant the crust breaks, all the way through the spike, the trapped fireball, the cooling tail, and the high-energy afterglow, you are watching magnetic energy get converted into radiation step by step. First in a violent dump that lights up the whole sky in gamma rays, then in a slower bleed of X-rays as the bubble contracts, then in extended afterglows as fast particles crash into the environment. And those afterglows carry a ton of information. They tell you about the density of the space around the magnetar, how much material got launched, and how efficiently the field accelerates particles. Which raises the next question. Once the main flash is over and the fireball begins to fade, how long does the echo actually last? What do the X-ray and radio afterglows look like in detail? And how can those fading signals still teach us about the explosion long after the spike is gone from the detectors? The spike is gone in a fraction of a second, the pulsating tail fades over a few minutes. But the magnetar is not done. For weeks to months after a giant flare, the star is still glowing in X-rays at levels way above its normal state. It's like the whole surface and magnetosphere are cooling down from a brutal overheat. Observations of magnetars like SGR 1900+14 and SGR 1806-20 show exactly this. A long, slow decay in X-ray brightness that can stretch over months. Right after the flare, the X-ray luminosity jumps, then over days, weeks, it slides down step by step until it settles back into the quieter level we call its quiescent state. What you're seeing in that long tail is the magnetar trying to get rid of leftover heat and magnetic stress. The crust has been shaken. Fractures have dumped energy into the outer layers, and the magnetosphere has been reconfigured. The surface is hotter than usual. Deeper layers have absorbed part of the flare energy, and the magnetic field is still adjusting. X-ray telescopes track that slow fade by measuring the spectrum and brightness over time, and when you model it, you get a picture of a crust and magnetosphere cooling back toward equilibrium after a huge disturbance. The exact way the light falls off with time tells you how the heat flows in and out of the crust, and how much extra energy was pumped into the star by the flare. For SGR 1806-20 in 2004, the echoes weren't just in X-rays. Radio telescopes saw an afterglow that brightened and then expanded over the following weeks. By taking high-resolution radio images again and again, astronomers could literally watch a nebula around the magnetar grow. The apparent expansion speeds came out at something like a third to maybe 70% of the speed of light. That means the flare didn't just shake the magnetosphere in place, it launched an actual outflow of material at relativistic speeds. Using the size, expansion rate, and brightness of that radio nebula, they could estimate how much kinetic energy was carried by that outflow, and how dense the surrounding gas had to be to slow it down and light it up. So the radio afterglow is basically the flare's shockwave made visible. Now compare that to the afterglows of classical gamma-ray bursts from faraway galaxies. Those cosmological GRBs can have afterglows that last for months or even years. Cross X-ray, optical, and radio bands, with a lot more total energy. In contrast, magnetar giant flares usually have weaker and shorter-lived afterglows. The X-ray tail is bright early on, but drops relatively quickly. The radio emission can be strong at first, but it also fades on shorter timescales than many long GRBs. When you have good multi-wavelength observations and you know the distance, that difference in afterglow behavior is one of the ways you can say this was a nearby magnetar flare, instead of this was a distant GRB powered by a collapsing star or merging neutron stars. Distance is where afterglows become really important for the borderline cases. For extragalactic candidates like GRB 2004-15A, the prompt spike alone could easily be mistaken for a regular short GRB. But follow-up observations in X-rays and radio help lock down the host galaxy. In that case, the afterglow pointed to the nearby starburst galaxy NGC 253. Once you know which galaxy the burst came from, you know the distance. With the distance, you can turn the observed brightness into a real energy output. Then you can ask, does this energy look like a magnetar giant flare or like a neutron star merger? Without that association, you'd be guessing. With it, you can put the event in the right box. That's why every afterglow matters much more than it might seem at first glance. The fading X-rays carry information about how much the crust was heated and how the magnetic field relaxed. The radio nebula tells you how much material was ejected, how fast it moved, and what kind of environment the magnetar lives in. High-energy gamma rays in the afterglow phase tell you how efficiently particles were accelerated in the shocks. Even the shape of the fading light curve holds clues about geometry, like whether the outflow was more like a narrow jet or a wide shell. Each one of these signals is like a page in a forensic report. And remember, for giant flares we don't have hundreds of examples. We have 3 classic local ones, plus a handful of good extragalactic candidates. That means every afterglow we catch is incredibly valuable. It's not just another burst in a big catalogue, it's a rare chance to reverse engineer how a magnetar flare works from the inside out. But there's a catch. Sometimes all we see is the fast spiking gamma rays, without a clear afterglow, and that makes things a lot harder. When that happens, how do you decide whether you've just seen a magnetar giant flare in another galaxy, or a completely different beast like a neutron star merger? Short gamma ray bursts are already some of the fastest events we know, and that's exactly what makes magnetar giant flares hard to separate from them. Classical short GRBs, the ones we now link to neutron star mergers, usually last less than 2 seconds, often just a few tenths of a second. Magnetar giant flares start with a spike that is also a few tenths of a second long. On a raw detector light curve, if you just look at that first spike, a giant flare in another galaxy can look almost identical to a merger happening billions of light years away. Same timescales, same kind of hard gamma rays, same sharp rise and fall. The detector doesn't know what engine produced the photons, it just counts hits. When people stepped back and looked at big GRB catalogues though, something interesting showed up. If you group bursts by how bright they are and how long they last, you see the usual 2 main classes, long GRBs from collapsing massive stars and short GRBs from compact object mergers. But on top of those, there's a little cluster of events that are extremely bright, very short, and look like they're coming from much closer than the typical cosmological bursts. Their properties line up with what you'd expect if a magnetar in a nearby galaxy fired off a giant flare and you mostly saw the spike. That's where the idea of a third class comes from, a magnetar flare class hiding inside the general GRB population. So how do you tell them apart in practice? You look for details beyond the spike. Giant magnetar flares tend to show a very sharp initial spike, followed by a spectrum that evolves from harder photons to softer ones, and when you're close and lucky, you also see a long tail with clear periodic pulsations at the magnetar's spin period, usually a few seconds. Short GRBs from mergers might have some spectral evolution too, but they almost never give you a long, clean, pulsating tail that goes on for hundreds of seconds. That kind of repetitive tail is basically a neon sign saying, there is a spinning neutron star right here, and it just dumped magnetic energy. Of course, you only get those extra clues when your detectors are pointed at the right place, have the right sensitivity, and stay on long enough after the spike. A lot of bursts don't have that level of coverage. For those, you have to rely on more subtle spectral differences, and that's messy. Some merger bursts are very short and very bright. Some magnetar flares in other galaxies are faint and borderline in our instruments. So you bring in the next big discriminator, distance. Energy estimates for these events depend completely on how far away they are. If you see a short spike and assume it's at a cosmological distance, say billions of light years, you get a huge energy output, the kind that fits neutron star mergers or collapses of very massive stars. But if that same spike actually came from a magnetar in a galaxy a few million light years away, the true energy is much lower. You can easily overestimate the energy by factors of 1,000 or more if you assume the wrong distance. That's why associating a burst with a specific host galaxy and measuring that galaxy's redshift is such a big deal. Once you know the distance, you can decide if it's only a giant flare or a full-blown cosmological GRB. This is where afterglows, and precise localizations earn their keep. An X-ray or radio afterglow you can tie to a galaxy like NGC 253 or to a region rich in young stars pushes you toward the magnetar interpretation. A burst localized to a faraway galaxy with properties that match merger models pushes you toward the classical short GRB camp. Without that context, you're trying to identify an engine from a single bright blip on a graph. All of this feeds back into the why only 3 question, because some magnetar giant flares almost certainly hide inside our catalogue of short GRBs. We know that the 3 local, clearly identified events are not the whole story. There are probably more giant flares sitting in the data, especially from nearby galaxies, that we just haven't labelled correctly because we lack a tail, or a host, or a good distance. When people do population studies and try to correct for that, they do find room for a small but real magnetar flare population mixed into the short GRB sample. Even after you account for that though, giant flares remain rare. Most short GRBs out there still appear to be true cosmological events powered by mergers. The magnetar group is a small minority, especially when you restrict the really extreme 2004 level explosions. So the statement, only 3 clearly seen nearby, holds up. Those 3 are just the clean examples where the universe gave us the full set of clues: spike, tail, pulsations, afterglow, and a good distance. So now the picture is this. On your detector, some of the shortest or brightest flashes you see are actually coming from 2 completely different kinds of engines: smashed neutron stars in distant galaxies and magnetic starquakes on magnetars much closer by. Untangling which means chasing after afterglows, host galaxies, and subtle timing signals. And that sets up the next step. If we now have at least one giant flare clearly pinned to another galaxy, like GRB 20415A in NGC 253, how does that expand the story beyond our local group? And what does it say about how often these magnetic bombs go off in the wider universe? In April 2020, the universe gave you a very compact clue from another galaxy. Satellites picked up a burst called GRB 20415A, a ridiculously short and hard spike of gamma rays, followed by a softer tail that lasted only about 0.2 seconds. When people traced it back on the sky, the position lined up with the starburst galaxy NGC 253, about 3.5 megaparsecs away, roughly 11 million light-years. That is still in our cosmic neighbourhood, but way beyond the Milky Way and its little companions, and yet, from that distance, the spike still slammed into our detectors with serious intensity. The light curve was fast even by short GRB standards. You had a millisecond scale hard spike, basically a hit that rises and falls in less time than you can say its name, followed by that softer emission over a couple tenths of a second. If you just looked at the first couple of frames in the data, you might call it a normal short gamma ray burst and move on. But when you add the localization to NGC 253, the timescales, and the spectrum together, it starts to look very familiar if you've been staring at magnetar flares for years. Once you know the galaxy, you know the distance. And with the distance, you can estimate the isotropic equivalent energy, the energy it would have if it radiated the same in all directions. For GRB 200415A, that number comes out around 1.3 times 10 to the 46 ergs. That is right in the same ballpark as the 2004 superflare from SGR 1806-20, which we already treat as the extreme upper end of known magnetar flares. So now you have an energy twin of that 2004 event, but this time clearly sitting in another galaxy. That combination, short spike, soft tail, nearby galaxy, energy around 10 to the 46 ergs, makes GRB 200415A basically a textbook example of an extragalactic magnetar, a giant flare. There was another key piece, the high-energy afterglow. The Fermi Large Area Telescope, which watches the sky for extremely energetic gamma rays, saw emission in the GeV range from this burst lasting up to about 1,000 seconds after the initial spike. That made it the first clear case where a magnetar giant flare candidate showed a GeV afterglow. Those GeV photons don't just appear for fun, they tell you that electrons and maybe other particles are being accelerated to very high energies in the magnetar's magnetosphere, and in the shocks as the outflow crashes into the surrounding gas in NGC 253. By modelling that afterglow, you can put limits on how strong the magnetic field has to be out there, how dense the medium is, and how much energy is in fast particles versus in the thermal fireball near the star. GRB 200415A didn't show up alone either. Once people understood that it was probably a magnetar giant flare, they started looking harder at other short bursts with similar properties. Events like GRB 180128A and GRB 231115A have been flagged as additional candidates. They're also very short, very bright, and likely associated with nearby galaxies rather than distant cosmological ones. The details vary, and not all of them have as clean a data set as GRB 200415A, but together they start building a small sample of extragalactic giant flare suspects. We're not talking about dozens or hundreds, we're still at the handful stage, but it's more than zero. That changes the way you talk about only 3 giant flares. The original 3 are still special, because they're in or very near the Milky Way and gave us full detail. Spike, tail, pulsations, afterglow, the works. SGR 0526-66 in 1979. SGR 1900 plus 14 in 1998. SGR 1806-20 in 2004. Those are the ones where we can see the magnetar itself and study the star in between flares. But now you can add GRB 200415A in NGC 253, plus a couple of other nearby candidates as extragalactic cousins. They expand the map from local group only to nearby universe. Even with that expansion, look at the big picture. across billions of stars in each galaxy, across all the supernovae, all the ordinary flares, all the long and short GRBs from mergers and collapses, magnetar giant flares still sit at the ultra-rare top of the pyramid. We are scraping together a sample by combining 50 years of monitoring, every working gamma-ray satellite, careful cross-checks with radio and X-ray telescopes, and deep searches through old data. The result is still just a tiny list of clear events and a small ring of suspects. So now the story has grown. 3 giant flares in and near our own galaxy gave us the basic physics. Then GRB 2004-15A and its relatives told us that the same kind of explosions are happening in other galaxies. At roughly the same energy scale, that means magnetar giant flares are not just a local curiosity. They are a real, but rare, part of how the universe moves magnetic energy around in many galaxies. And once you know that, the next logical question is, how rare exactly are they compared to all the other explosions in a galaxy like the Milky Way? Can you actually put numbers on their rates? And do those numbers line up with the only 3 in 50 years we see in our neighbourhood? If you want to know how rare giant flares really are, you first have to ask how rare magnetars themselves are. In the Milky Way and nearby galaxies, we've only identified around 30 magnetars so far. By contrast, we know thousands of ordinary neutron stars that show up as radio pulsars, spinning and beaming radio waves at us. And that's just the visible tip. Population models say the galaxy has borne hundreds of millions of neutron stars over its history. A good fraction of those probably went through a magnetar phase early on. Here's the key detail. The magnetar phase doesn't last forever. As the magnetic field decays, the star cools down and the bursts stop. The object doesn't disappear, it just becomes a quiet neutron star that's hard to detect. So models suggest there could be tens of millions of dead or dormant magnetars lurking quietly in the Milky Way, with only a tiny fraction currently active enough to give off bursts in X-rays or gamma rays. The 30 or so magnetars we see are like the loud teenagers in a city full of retired elders. Now focus on the active ones. Out of those, how often does a single magnetar throw a true giant flare, not just a regular short burst? If you take the handful of known flares, fold in how long we've been watching, add in upper limits from big structures like the Virgo cluster where we've stared with gamma ray instruments for tens of millions of seconds and not seen anything similar, you get a rough answer. It looks like a given magnetar might only produce one really huge flare with energy above a few times 10 to the 45 ergs every few hundred years. Not every decade, not every lifetime, every few centuries at best. That per magnetar rate is already low. Now spread it across a whole galaxy. In a Milky Way-like galaxy, you might have something like 30 magnetars in an active bursting phase at any given time. Multiply one every few hundred years per magnetar by a few dozen magnetars, and you get roughly one really big flare per few decades to a century for the whole galaxy. That lines up almost perfectly with what we've actually seen. In about 40 to 50 years of good gamma ray monitoring across the local group, we've caught 3 giant flares close enough to study in detail. One from another galaxy next door, 2 from inside our own. That's exactly the kind of numbers you'd expect from those rate estimates. To really see how extreme that is, compare it to other big cosmic explosions. The Milky Way probably has a core collapse supernova roughly every 50 to 100 years. We haven't seen one directly in visible light for centuries, but that's mostly because of dust and unfortunate angles. Neutrino detectors and future surveys will probably catch the next one. Supernovae are rare in human terms, but they are regular events on galactic timescales. Giant magnetar flares look to be at least as rare, may be rarer, and that's even though they're actually easier to see through dust. High-energy gamma rays don't care about dusty clouds the way visible light does. They punch right through. If giant flares were happening all the time in our galaxy, our satellites would have a crowded highlight reel. Instead, they have 3 local showpieces. You can also put them next to classical gamma ray bursts. Our detectors have collected thousands of GRBs from across the observable universe. Long GRBs from collapsing massive stars, short GRBs from mergers, plus a bunch of ambiguous ones. Against that huge background, magnetar giant flares make up a tiny fraction. You have to comb through all those events very carefully to find the small subset that look like nearby magnetar flares rather than distant mergers. That's how far out on the tail of the distribution they sit. So when you hear rarest thing in the universe, only 3 found in this context, it's not just a dramatic slogan, it's a statistical statement. You're talking about events that require a very specific object, in a very specific magnetic state, with a crust that has built up the right amount of stress in the right phase of its life that then fails in exactly the right way and beams a big fraction of its energy in our direction, and does it during the short slice of history when we happen to have gamma-ray satellites running. All of those filters stacked together give you a tiny number of detections. Each giant flare ends up being a once-in-a-civilization lab experiment in extreme physics. You don't get to repeat it next week. You might not get another one in your lifetime. When one happens, the data from that single event can keep theorists busy for years, because it's one of the few chances nature gives us to test our models of matter at nuclear densities, magnetic fields at 10 to the 15th Gauss, and quantum electrodynamics in crazy regimes. But there's a very natural follow-up question hiding behind all this number crunching. If these things can release that much energy in our direction, even from tens of thousands of light years away, what happens if a giant flare goes off much closer to us? How close is too close for life on Earth? And are there any magnetars out there that we actually need to worry about? The 2004 flare from SGR 1806-20 is not just a crazy story about distant space. It is also your calibration point for how dangerous is this really? That magnetar sits around 50,000 light-years away on the far side of the Milky Way, yet for a fraction of a second it was the brightest source of gamma rays in the sky after the Sun. Our satellites saw detectors saturate, and Earth's upper atmosphere actually changed. The ionosphere got an extra dose of ionization. Electrons were stripped from atoms, and radio propagation shifted. No mass extinction, no global disaster, but a clear physical effect on our planet from a single flare half a galaxy away. That's your real data point for damage versus distance. From there, people run models. They take the energy of the 2004 flare, scale it with distance, and ask what happens if the same thing goes off closer. The numbers land in a simple but serious range. A 2004-style giant flare within a few thousand light-years could probably hit our atmosphere hard enough to significantly deplete the ozone layer, at least temporarily. That means more ultraviolet light from the sun reaching the surface, which could stress ecosystems and increase mutation rates. If you move the same event to within something like 100 light-years or less, many studies say it could be outright catastrophic for complex life. With major ozone loss and a big spike in harmful radiation at ground level, the exact thresholds depend on details of the flare, the direction of any beaming, and the state of Earth's atmosphere at the time. So there's uncertainty, but the basic picture is physically reasonable. So the next question is obvious. Do we have any magnetars that close? Right now, with all the surveys and follow-up observations we've done, We don't know of any hyperactive magnetars within a few hundred light years of Earth. The magnetars we've identified tend to live in very different neighbourhoods than the Sun. They are mostly tens of thousands of light years away, often in crowded star-forming regions or near the galactic centre, places where massive stars are born and die quickly. Our Sun sits in a relatively quiet patch of the disk, with older stars and less massive star formation. That doesn't mean there are zero risks, but it does mean there is no obvious loaded gun magnetar sitting just down the street. To get a sense of risk, it helps to rank magnetar giant flares against other cosmic threats. Nearby core collapse supernovae are a more standard concern. A supernova within a few tens of light years could also damage the ozone layer and flood Earth with high-energy radiation over weeks to months. Long-duration gamma-ray bursts from collapsing massive stars are even more intense along their jet axes, but they seem to be rare in galaxies like the Milky Way and are usually aimed somewhere else. Magnetar giant flares are different. They're insanely bright in gamma rays, but they don't blow up the star, and the really dangerous zone around them is smaller because the energy is lower than a full GRB and released in a shorter burst. On very long habitability timescales, they are probably a minor contributor compared to supernovae, big GRBs, or just the slow changes in a star and a planet's own climate. That doesn't make them boring, it actually puts you in an interesting position. Your civilization exists at a time when gamma-ray satellites are in orbit, with enough sensitivity to catch these ultra-rare events. But you're not parked next to a ticking magnetar that could strip your atmosphere. You're far enough away from the known active ones to be safe, yet close enough in cosmic terms that 3 giant flares in your local group have already lit up your detectors in the last few decades. That's a very specific window. Too early in history, no satellites. The flares happen and no one ever knows. Too close to the wrong magnetar, and you get the energy lesson the hard way. So you end up in this arrow zone where giant flares are scary on paper, but in practice they are mostly a gift. Rare clean experiments in extreme physics that you can study from a safe distance. And that leads to a natural comparison. Magnetars are clearly extreme, but how do they really stack up against the other monsters you hear about all the time, like black holes? Which one wins on things like magnetic field strength, brightness, and pure "this should not be possible" factor? When people talk about extreme objects, black holes usually get all the attention. But if you care about raw magnetic insanity and fast violent outbursts, magnetars actually win in a few key categories. The two objects live in the same universe, but they play very different games. Start with magnetic fields. A black hole by itself, in the strict sense, doesn't carry its own built-in magnetic field. Any field you see near a black hole comes from the plasma swirling around it, from disks, jets, and surrounding gas. Those fields can be strong, especially near the event horizon of a supermassive black hole, but they're not the black hole's field in the way you might think. A magnetar, on the other hand, has its magnetic field anchored directly in its matter. The crust and core carry currents that generate a surface field around 10 to the 14 or 10 to the 15 Gauss. That's 1 trillion times stronger than Earth's field. As far as we know, magnetars are the strongest actual magnets in the universe. Full stop. Now talk brightness. There's a concept called the Eddington luminosity. It's basically the point where the outward push of radiation on matter balances the inward pull of gravity. For a typical neutron star, that limit is around 10 to the 38 ergs per second. If you keep piling on more luminosity in normal circumstances, radiation pressure should start blowing material away, but during a giant flare, a magnetar blows straight past that limit by factors of 1,000 or more in terms of peak luminosity. How does it get away with that, without tearing itself apart? The answer is that the plasma is confined by magnetic fields, not by gravity alone. The field lines trap the hot particles and photons, so the usual Eddington argument doesn't apply in a simple way. The star can go super Eddington for a short time because magnetism is doing a lot of the confining work. Then there are the timescales. Black holes can be bright for a long time. When a star gets shredded by a supermassive black hole, or gas suddenly floods an accretion disk, you can get flares that last days, weeks, even months. The peak brightness can be huge, but it's spread over a long period. Magnetar giant flares are the opposite style. They hit a similar or higher peak luminosity for a fraction of a second, maybe 0.2 seconds, then they drop into a tail that fades over minutes. One is a slow burn, the other is a snap. In terms of peak power, magnetars can rival or exceed many black hole flares, but they do it in a single burst that's over before you can even react. Now people are starting to ask the next level questions, not just how bright is it, but does it shake space-time? Does it spray out neutrinos? Giant flares involve a sudden rearrangement of mass and magnetic fields, plus starquakes that shake a 20-kilometer object at high frequencies. That's the kind of thing that could in principle produce gravitational waves. They also involve dense nuclear matter, which is a potential source of neutrinos. So far, detectors have not clearly seen gravitational waves or neutrino bursts linked to a magnetar giant flare. What we have instead are upper limits, constraints that say if they emitted these messengers, it was below this level. Even that is useful. Giant flares are becoming testbeds for multi-messenger physics, giving you real events where you can search gravitational wave and neutrino data around known times and refine your models. There's one more way magnetars differ from black holes that matters for how you relate to them. A black hole's defining feature is its vent horizon, which can be the size of a city, a country, or larger than the solar system if it's supermassive. It's hard to picture in any concrete way. A magnetar is only about 20 kilometers across. That's smaller than most big cities. Yet inside that volume you cram more mass than the sun, plus a magnetic field that would rip apart normal atoms, plus a crust that can crack and launch a giant flare. It's an object with cosmic-level violence packed into a size you can easily imagine. That scale makes magnetars feel almost local in your mind. You can think about a city-sized sphere, with a surface, a crust, specific spots where cracks form, hotspots that rotate in and out of view every few seconds. That mental picture helps when you think about the 3 rare giant flares we've seen. These aren't anonymous flashes from somewhere in the void. They're specific, city-sized stars doing something extreme in a very short time. So on this scoreboard, magnetars beat black holes on raw magnetic field strength. They match or beat them on peak luminosity over short times, and they give you a physically tangible object to focus on. Black holes still own the game when it comes to gravity and long-term accretion, but magnetars own the game of rapid, magnetic, all-or-nothing outbursts. And that raises another question. If magnetars are born from massive stars that exploded not that long ago, can you actually see the debris fields from their births? And can those supernova remnants and the elements they made tell you anything about how these rare giants live and die? When you look around magnetars in more detail, you don't just see isolated stars, you see crime scenes. Take SGR 0526-66, the one behind the 1979 flare. It sits inside a bright supernova remnant called N49 in the Large Magellanic Cloud. That shell of gas is the debris of a massive star that exploded a few thousand years ago. Right at its centre, you have the compact core, now acting as a magnetar. That's a clean link. Big star dies in the core collapse supernova. leaves behind an ultra-magnetized neutron star that later fires a giant flare. Other magnetars show the same pattern, sitting in or near young remnants, telling you they're the fresh products of recent explosions, not ancient relics. Because these systems are young, you can try to age them in two ways. One is by looking at the size and expansion rate of the supernova remnant. The other is by watching the magnetar's X-ray emission fade over years and decades, building a cooling curve. For objects like SGR 0526-66, those curves tell you something important. Magnetars stay hotter for longer than normal neutron stars of similar estimated age. Their surfaces emit more X-rays than you'd expect if they were cooling passively. The obvious conclusion is that something inside is still heating them. That something is magnetic field decay. As the field slowly unwinds and rearranges, it dumps energy into the star, keeping it warmer than a quiet neutron star of the same age. Once you start tying magnetars to supernovae and to recent star formation, another question comes up. Do magnetars and their flares actually help build some of the heavy elements in the universe? Recent work has played with the idea that under the right conditions, magnetar flares and related outflows could be neutron-rich enough to do rapid neutron capture, the process that builds gold, platinum, and other heavy elements. Some estimates say magnetars might contribute a noticeable fraction, maybe up to around 10%, of those elements if their flares and winds regularly throw out the right kind of material. But this is not settled. It depends on details of the outflow, composition, and how often the right kind of flare happens. Right now it's an active research topic, not a done deal, so you should file it under interesting possibility rather than established fact. There's a similar forensic vibe much closer to home. On Earth, people have found sudden spikes in certain radioactive isotopes in tree rings and ice cores, especially carbon-14 and beryllium-10. These spikes suggest that at some points in the last few thousand years, Earth got hit by bursts of high-energy particles or radiation stronger than normal solar activity. The leading suspects are huge solar superflares or unusual solar events. But in some discussions, a nearby magnetar flare also appears on the suspect list. The idea is that a not-too-distant flare could bombard the upper atmosphere with gamma rays and cosmic rays, tweaking the production rates of those isotopes. The problem is, the data don't come with labels. You see the spike in isotopes, but you don't see a date stamped magnetar versus Sun. So far, nothing clearly points to a magnetar. It's a forensic whodunit with multiple possible culprits. All of this shows that a giant flare is more than a one-frame flash on a satellite readout. It's connected to a full life story. A massive star forms, lives fast, explodes as a core collapse supernova, leaves behind a magnetar. That magnetar stays hot longer than normal because its magnetic field keeps decaying and feeding energy into the crust and core. Occasionally it cracks its crust and fires off bursts and maybe a giant flare. In the process, it might contribute some heavy elements to the galaxy, and it definitely sends high-energy radiation and particles into its surroundings. Some of that debris ends up mixed into the interstellar medium, the raw material for future stars and planets. So each rare giant flare could leave traces in more than just our detectors. It might leave chemical fingerprints in the gas around it, in the composition of new stars, maybe even in planetary atmospheres if it goes off close enough. When you connect magnetars to their supernova remnants, to their cooling histories, to possible nucleosynthesis and isotope signatures, you start to see them as tools for cosmic archaeology. They're not just explosions, they're events that record and rewrite the history of matter in their neighbourhood. And that leads straight into another big mystery where magnetars have suddenly stepped into the spotlight. We've been picking up fast radio bursts, ultra-short, intense flashes of radio waves from across the sky for years. They look completely disconnected from everything else at first. But now we have a direct link between one magnetar and one of those bursts. So if magnetars can shake stars, heat crusts, maybe forge elements, can they also be behind at least some of the fast radio bursts we keep seeing? On 28th of April 2020, one magnetar in our own galaxy finally connected two big puzzles. The source was SGR 1935 plus 2, 154. Radio telescopes on Earth picked up a very bright, very short, fast radio burst, now called FRB 200428. At almost the same time, multiple satellites in orbit saw an X-ray burst from that same magnetar. The timings matched, the sky positions matched, and there was no serious way around it. For the first time ever, we had a fast radio burst and a magnetar flare happening together from the same object. That was the smoking gun people had been waiting for. Fast radio bursts, FRBS, had been confusing astronomers for years. They are millisecond-long flashes of radio waves coming from far outside our galaxy, often from billions of light years away. Their radio energies are huge. They just switch on, dump a ton of radio power, and switch off. Before 2020, as there were many theories about what could cause them, and magnetars were on the list, but there was no direct proof. FRB 200428 changed that. You suddenly had a known galactic magnetar doing something that looked like a scaled-down version of the cosmological FRBS, with radio and X-ray activity tied together. In terms of radio energy, FRB 200428 was weaker than the giant extragalactic FRBS we see from other galaxies, but weaker here still means enormous. It was more than 1,000 times stronger than the brightest giant radio pulses we've ever seen from famous pulsars like the Crab. For a neutron star inside the Milky Way, that is extreme. So even though it doesn't reach the insane energies of FRBs from billions of light years away, it sits clearly in between normal pulsar behavior and the most powerful known radio flashes in the universe. That makes it a perfect bridge case. It shows that magnetars can produce far B-like bursts, at least in some circumstances. So what does that say about giant flares? The link between SGR 1935 plus 2, 154 and FRB 200428 strongly suggests that at least some FRBS are produced during magnetar flare activity. Maybe during the early stages of a flare, when the magnetic field is rearranging very fast. Maybe in shocks where the flare outflow hits surrounding plasma. There are several models on the table, but they all share one core idea. Magnetic energy in a magnetar can be converted not just into gamma rays and X-rays, but also into very coherent radio emission. That means every magnetar flare you see, especially the giant ones, becomes a possible lab for testing FRB physics. If you can catch a giant flare with radio telescopes and X-ray satellites at the same time, you can ask directly, did this flare launch an FRB too? But here's the catch. Not every flare from SGR 1935 plus 2, 154 makes a fast radio burst we can see. This magnetar has had many X-ray bursts, including bursts with similar X-ray properties to the one that produced FRB 200428, and most of them have not been seen as FRBS in radio. That tells you the conditions for making a fast radio burst are more specific than just magnetar flares. Maybe the radio beam is very narrow, so most bursts simply don't point at Earth. Maybe you need a particular combination of magnetic twist, particle density, and shock geometry. This mirrors what we saw with giant flares. Magnetars throw lots of small tantrums, but only rarely line up everything for a truly extreme event. So magnetars are starting to look like multi-channel senders. A single outburst can show up in several kinds of messengers. Gamma rays in the initial spike, X-rays in the tail and the long cooling phase, radio waves in FRB like bursts or in the slower afterglow nebula, maybe neutrinos if the internal physics is right, maybe gravitational waves if the starquake is violent and asymmetric enough. We haven't definitively caught neutrinos or gravitational waves from a magnetar giant flare yet, but we are actively looking. Every time a big flare goes off, people dig into data from detectors like IceCube and LIGO around that time window to see if anything else twitched. That turns each giant flare into a multi-messenger test. Even non-detections tell you something. If you see no gravitational waves above a certain level, you can say, okay, the starquake can't be shaking the star this hard in an uneven way. If you see no neutrinos, you get limits on what's happening deep in the core and in any outflows. If you do see a radio burst at the same time, you gain one more piece of the puzzle for how FRBS work. Each channel fills in a different part of the diagram, from crust fracture to magnetosphere dynamics to particle acceleration far away from the star. So magnetar giant flares move from being just 3 weird gamma events to being potential full-spectrum sirens. They might light up your gamma-ray detectors, your X-ray monitors, your radio telescopes, and maybe in the future your neutrino and gravitational wave observatories too. The problem is simply that they are so rare that we haven't had enough of them to explore all of those channels at once, and that leads straight into the next big set of questions. If you only have 3 classic giant flares to work with, plus a small handful of candidates, how much can you really say about what triggers them, why some magnetars blow and others don't, and what exact combination of magnetic field strength, crust stress, and internal structure pushes a magnetar over the edge into a giant flare instead of just another small burst? For all the detail we've pulled out of those 3 giant flares, the basic trigger is still not fully nailed down. Theory has a short list of suspects, but not a final verdict. Recent modelling tries to be very specific about the conditions where a magnetar crosses the line from normal bursting to giant flare. In those models, you track the internal magnetic field as it slowly twists and shears the star over thousands of years. You dial in the overall field strength, how much the field is twisted relative to a simple dipole, and how strong the crust is before it breaks, the yield stress. When you pick combinations in the right range, the simulations can actually reproduce light curves that look a lot like the 3 classic flares: fast spike, decaying tail, right kind of total energy. So we know we're in the right ballpark. The problem is, there's still more than one way to make it work on paper. One of the big debates is where the instability really starts. One camp says the root cause is deep inside the star. In that picture, the internal magnetic field gets so tangled that it becomes unstable. That instability rearranges the field in the core, sends shear waves up into the crust, cracks it, and then the magnetosphere responds with reconnection and a flare. Another camp puts more weight on the outside. There, the idea is that the magnetosphere itself, the region of field lines and plasma above the surface, slowly builds up twist until it hits a critical point. Then the external field reconnects and snaps to a lower energy configuration, and that sudden change sends stress back into the crust and triggers a starquake. Both pictures involve crust failure and magnetic reconnection, but they disagree about what moves first. People try to use observations to choose between them. Rise times of the initial spike matter because they tell you how fast the energy release ramps up. Spectral evolution in the first fractions of a second matters too, because it encodes how quickly the plasma becomes optically thick and how the field changes. If the flare is driven from deep inside, you might expect slightly different timing and spectral signatures than if it starts as a magnetospheric reconnection event that later couples into the crust. With only 3 really good examples, and a lot of noise and detector saturation in the brightest parts, the data can be made to support both sides in different ways. So for now, internal versus external trigger stays an open question. Another puzzle is why only a minority of known magnetars have ever shown giant flares. We know a few dozen magnetars. We know at least some of them have strong enough fields to fit the magnetar label. Yet only 3 have produced the kind of flare we're talking about in our local group, and only a handful more are good candidates in other galaxies. That suggests there are extra parameters in play that we don't measure directly. The internal geometry of the magnetic field might be different from star to star. Even if the surface strength looks similar, the age of the magnetar could matter. Maybe giant flares prefer a certain age window where the field is strong but not completely locked in. The properties of superfluid components in the core might change how stress is transmitted. Even the external environment, like how much plasma is sitting in the magnetosphere, could decide whether a big rearrangement turns into a giant flare or just a lot of small bursts. To really answer these questions, we need more than 3 events. That's where future observatories come in. Upcoming missions and all sky monitors are being designed to watch more of the sky, more of the time, with better energy coverage and faster timing. The goal is simple: catch more magnetar flares. Some will be small, some moderate, and if we're lucky, a few more giant ones. With a bigger sample, you can actually do statistics instead of just storytelling. You can ask whether certain spin periods, field strengths, or environments are overrepresented among giant flare sources. You can see whether there are clear subclasses in light curve shapes, and you can coordinate better with radio, neutrino, and gravitational wave detectors to grab the full multi-messenger picture when the next big one hits. The stakes here are high even if the event count stays low. Giant flares push several branches of physics to their limits at once. They test quantum electrodynamics in ultra-strong magnetic fields, where the vacuum itself bends light and lets photons split. They probe nuclear physics at insane densities in the crust and core, where matter behaves in ways we cannot reproduce in any lab. They exercise magnetohydrodynamics in curved spacetime, with magnetic fields, plasma, and gravity all strongly coupled in a tiny volume. Every new flare we catch has the potential to falsify parts of our models. If the next one has a different spectrum, or a different set of oscillation frequencies, or a different spike-to-tail energy ratio, we have to adjust the theory. So giant flares sit in this interesting spot. We kind of know what they are, we kind of know why they should exist, and we can build models that match the 3 big ones we've seen. But we don't yet know why they happen when they do, why some magnetars never seem to cross that line, or whether our current recipe is missing a key ingredient. Each future flare is not just another data point, it's a potential breaker of assumptions, and that brings us back to you. After all this, what do these 3 rare explosions actually change for your picture of the universe? How do they take you from vague ideas about violent space to a concrete understanding that 3 specific flashes in 1979, 1998, and 2004 quietly rewrote our view of extreme matter and magnetic fields? So here's where everything you've heard snaps together. In 1979, in a small companion galaxy called the Large Magellanic Cloud, a super bright gamma ray flash hit a bunch of spacecraft that weren't even built for this job. That was SGR 0526-66, sitting inside the supernova remnant N49. Then in 1998, in the direction of Aquila, SGR 1900 plus 14 lit up our detectors so hard that some of them saturated, even though it was about 20,000 light-years away. And in 2004, towards Sagittarius on the far side of the Milky Way, SGR 1806-20 fired the most violent flare of them all, with a spike so intense that it temporarily became the brightest extra-solar gamma-ray source we've ever seen. 3 different magnetars, 3 monster explosions, each one caught by a patchwork of satellites that were doing their own missions, got slammed by a wave of gamma rays, and somehow kept recording. At first, events like the 1979 flare were just, what the hell is this spikes in gamma ray data? Detectors originally put up to watch for nuclear tests suddenly saw something way brighter, coming from deep space. Then we saw the same pattern in 1998 and 2004, and each time the details kept lining up. A tiny fraction of a second for the spike, a pulsating tail lasting minutes, pulse periods of a few seconds that match a rotating neutron star, total energies up to around 10 to the 46 ergs, and spectra that look like a hot plasma trapped in a huge magnetic field. Those 3 flashes pushed us from anomaly to framework. They forced the idea that there exists a special kind of neutron star, with magnetic fields up in the 10 to the 14 or 10 to the 15 Gauss range. City-sized objects whose magnetic energy rivals or beats their thermal and rotational energy. They made magnetar go from a speculative label to a working model. They told us that the crust of such a star can actually crack, that the crack launches starquakes and triggers magnetic reconnection, and that this process creates a compact fireball of electron-positron pairs and gamma rays, trapped by the field and pulsing as the star spins. From the tails of those flares, we picked out quasi-periodic oscillations, those little wiggles at tens to hundreds of hertz, and used them as seismology tools to probe crust thickness and core physics. From the long X-ray decays, we measured how magnetars cool and how magnetic energy keeps heating them. From the radio afterglow of SGR 1806-20, we tracked an expanding nebula moving at a big fraction of the speed of light and measured the kinetic energy of the outflow. In other words, 3 spikes in some satellite timelines turned into a full physical picture of ultra-magnetized neutron star, their interiors, their magnetospheres, and their explosions. And then the story widened. Once we had that framework, giant flares stopped being just rare curiosities and started being tools. GRB 200415A and NGC 253 showed that the same kind of flare can happen in another galaxy with almost the same energy as the 2004 event. That let us use giant flares to probe star-forming galaxies a few megaparsecs away, without needing a supernova you can see in visible light. The FRB 2004-2 event from SGR 1935 plus 2154 showed that magnetar flare activity can produce fast radio bursts, suddenly tying FRBS to magnetars and turning every future giant flare into a lab for radio emission physics. On the high-energy side, giant flares let us test quantum electrodynamics in fields where the vacuum itself acts like a polarizing medium, and where photons can split or merge in ways that barely matter anywhere else. On the dense matter side, their starquake signatures let us test models of nuclear physics at densities far beyond atomic nuclei, where you might have superfluid neutrons, superconducting protons, and exotic phases of matter. On the astrophysics side, they give us rate estimates and constraints for how many magnetars are out there, how often they flare, and how much they might contribute to heavy elements or to the high energy background. So the rarest thing in the universe, at least in this corner of it, quietly anchors a bunch of our current understanding of extreme astrophysics. You don't need thousands of examples if each example is this rich. The universe handed us 3 clear local giant flares, plus a few extragalactic cousins, and in return we've squeezed them for every bit of information we can get. What you're left with as you sit here is a very specific picture. Somewhere in the Milky Way right now, there are magnetars slowly twisting themselves toward their next big failure. Their internal magnetic fields are creeping, their crusts are under stress, their magnetospheres are loaded with plasma. Most of the time, they vent that energy as small X-ray bursts that almost nobody hears about. Very rarely, one of them will cross the threshold and fire a giant flare. That next flare might go off on the far side of the galaxy, or in a satellite galaxy, or in some other nearby system that we'll only recognize by its spike and tail. You might see one more of these in your lifetime, or you might not. The rates say it's a coin toss on human timescales, but the fact that we've already seen 3, and that we were lucky enough to have satellites running at exactly those times, means you are watching the universe in a very particular era. An era where even the shortest, rarest, most extreme explosions are no longer just silent events that happen unnoticed. They leave digital fingerprints, they trigger automatic alerts, they get dissected by teams all over the world. So next time you think about violent space, don't just picture vague explosions, picture 3 very specific moments. March 1979, August 1998, December 2004. 3 magnetars, 3 city-sized stars with insane magnetic fields, each one snapping hard enough to light up a galaxy in gamma rays for a fraction of a second. Those are the flashes that rewrote the universe in your head, even if you only just found out they happened. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.